So having looked at ways to hack beams in longitudinal cross-sectional directions, our next step is to look at what happens when we take section active principles and blow them up beyond beams. And we'll look at two types that are very related in the way they work and their sort of mechanics. The simplest type is folded plates, and then we'll go on to look at long vaults, or what happens basically when we take folded plates and make them out of curved surfaces. Related, but with some subtle differences between the two. A folded plate is essentially a thin sheet, usually of concrete, but it could be of steel or it could be of timber, that we have arranged so that it has some sectional depth to it. So you can think of this as having two important dimensions. One is the actual thickness of the plate itself, often just a couple of inches if it's in concrete, maybe even thinner if it's out of plywood or steel. And then there is a kind of height to the fold itself. So you can see here we have a folded plate that has a thickness of maybe a couple inches of concrete, but then it also has a height, the kind of height of that triangle, which is basically the effective depth of the folded plate. And if you want to think about this in terms of section active members, that's basically the depth of the beam that the folded plate is creating. When we design a folded plate, we're usually designing some kind of roof. We're usually taking a section active principle and trying to stretch it out to also being an enclosure. And what we want is we want to get a vertical separation between the high points of the fold and the low points of the fold. And what that does is it takes that thin plate and it gives it the section modulus of a much, much deeper beam, right? So we're basically making beams. We're trying to make I-beams, but instead of concentrating the material in the flanges, we're spreading the material out so that we're getting two functions usually. One of them is the structural function, the carrying function over the span, and the other very often is enclosure, right? We're using folded plates often to shelter a space below. So the reason we would do this is that, first of all, they're thin, relatively efficient, and because we're combining these two functions, we're sort of killing two birds with one stone. We can design them to be very effective, very efficient in how they carry a load over a span. And because all we're worried about really is the depth, we have a huge range of options for what the geometry of the folded plate can be. And that might be responsive to programmatic issues. We may have some areas that want more height or less, maybe responsive to things like mechanical systems, or it could even be responsive to, say, solar conditions, where maybe we're looking to bring in north light, and we can design the folds so that there are openings that bring in the right kind of daylight. The great advantage structurally is that we're achieving the effectiveness basically of a very deep beam with much less of the material. Right? We're taking the same principle that we were looking at in hacked beams. How do we take dead weight away from the structure? And with a folded plate, basically, we're wrapping the structure around a programmatic space. And again, the important thing is that the folds give us a little bit of depth, right? Give that plate some section modulus. I like to think of it as taking a thin sheet of concrete or timber or steel and kind of tricking it into thinking that it's actually a very, very deep structural member. So here in these diagrams, you can see the kind of typical mechanics of a folded plate. Here in the upper left, you can see that these lines of force are showing you where there is compression and where there is tension. The simpler way to think about it, I think, is to just think of the folded plate as having kind of a region that is like a compression flange up at the top, a region that is like a tension flange down at the bottom, and then a region between them that basically functions as the web. And unlike an I-beam where we have very distinct regions, we can point very specifically to the flanges, we can point specifically to the web. In a folded plate, those are a little blurrier, that we don't have really necessarily really clearly defined flange and web areas. But keep in mind that the mechanics are basically the same, that we're looking for a kind of area at the top that's going to usually be in compression, an area at the bottom that's usually going to be in tension, and then an area between that's essentially holding those two flange areas stiff relative to one another, right? Making them work together. And also across the folded plate, we're resisting shear. We're resisting the tendency of the compression and tension elements to slide past one another. So one other way to think about this, right, is to just look at a simple sheet of paper, right, a piece of paper that has basically no structural property, right, no section modulus. But if we just put a little fold into it, right, we're holding it here with my fingers and thumb, and you can see that basically what I've done is I've made the paper take on a vertical dimension. And now, even though that's a very, very thin sheet, the shape itself is going to have a little bit of section modulus. There's an area at the bottom that, because this is a cantilever, this area at the bottom is going to go into compression. These at the top are going to go into tension. And if I take my sort of test weight here, you can see that the folded plate is going to carry that pen. The paper has gone into bending, not across its thickness, but instead across the depth of the fold that I've given to it. Right? This is the kind of simplest folded plate imaginable. Notice though that I'm having to do a little bit of work, right? My fingers and thumb are forcing the paper to hold that shape. And this is something that we'll see again and again, both in section active long spans, but also especially when we get to shells, that there's not only the kind of macro structural performance, but there are usually structural elements that are forcing the shape or forcing the material to maintain the shape that we want. So in the case of the folded piece of paper, that's my fingers and thumb holding the paper and forcing it to take on that fold. You can see here in these examples, we have these edge stiffening beams, horizontal beams that are going parallel to the span. And what those are doing is they're preventing the flat plate from bowing out, right, from bending and therefore eventually from buckling. You could imagine that if that edge stiffener wasn't there, those last folded elements could start to flatten out. And as they would flatten out, sort of expanding sideways, they would start to lose the depth. They would lose the section modulus that we've given them, and the folded plate would collapse. Right? Same with the piece of paper that we can hold with our hands. If I let that go, right, if I sort of let my fingers go, you see that the paper flattens out, loses its section modulus, and can't even carry its own weight. So we'll constantly be looking for these kind of primary structural elements, in this case the plates themselves, and we'll also be looking for the secondary elements that force those structural elements to maintain their shape, that usually prevent them from flattening out. So the paper and pen is kind of the simplest possible kind of desktop experiment you can do. But the other thing that we are maybe familiar with is the actual folded piece of paper that can hold usually like the weight of a book. And when we do this, what's happening again is that we're putting some of that paper into tension now, right? This is a simply supported beam, so tension is going to be on the bottom. And we have an area at the top that's going to go into compression. Right? Again, you can think of the top and bottom fold as being analogous to the flanges on an I-beam, and the piece of paper between is basically functioning as a web, taking up the shear forces, making those two flanges resist together. Now, if you think through this scenario here, the book on the folded piece of paper, very quickly you realize what will happen, right? The piece of paper will flatten out. It'll spread out, it'll flatten out, and the book will collapse. What we're missing in this drawing is that edge stiffener, or the horizontal beam, the stiffening structure that's going to keep the folded plate in its geometry, right? That's going to force it to stay in the structural geometry that we want. So folded plates began to be very popular in the 40s and 50s. Concrete long span construction was used for things like aircraft hangars. Here are a couple of early ones that have all of the components we've just talked about. So here on the left, this was at Miami International Airport, and you can see that what the engineers have done is they've taken a very, very thin shell of concrete, probably 2.5 to 3 inches thick, and they've arranged it with these deep folds, these kind of hexagonal folds, so that if you turn the hanger on its side and look at it in section, you can see what looks like a familiar double cantilever shape, right? Deep over the supports, tapering out to nothing over the ends. But if you look closely, you can see that that cantilever shape isn't solid. What we're looking at, the light line on the top, is the profile in elevation of that top fold. And what we're looking at the bottom is the section cut through the bottom of the plate there. So again, we've taken a very, very thin element that couldn't probably hold its own weight over that cantilever span. We've given it those folds, sort of tricking it into thinking that it's a much, much deeper structural element. And then if you look closely, you can see that we have a beam here at the back, right? Columns supporting this collar beam. And what that collar beam is doing is it's providing the stiffness to the concrete that prevents it from flattening out, and therefore losing its depth, losing its section modulus, losing its ability to span. And this principle applies to other materials as well. This is a hangar at San Francisco Airport by the engineer Lev Zetlin in 1970. And you can see that what Zetlin did is he took, this is just corrugated steel, right? Very, very thin, just a fraction of an inch thick. And he's twisted each one of those steel sheets into this form that goes from a very deep triangle at the root of that cantilever roof out to a very shallow triangle at the end. And again, if you look at this in profile, what you can see is that we have a cantilever shape deep over the root, skinny at the end, but that cantilever shape is just made up of very, very thin corrugated steel sheeting. And so you get all of the depth of that shape, but you're reducing almost all of the weight. You're taking out almost all of the weight of that solid cantilever, and you're basically making it a hollow shape. You're folding that steel sheet to conform to a typical cantilever shape. Again, sort of tricking it into thinking that it has a lot of depth, and in fact, it has almost no thickness whatsoever. And so typical static shapes, but when we look at the actual detail, we find that they're made up of very thin sheets of material. Now, the great advantage to folded plates is that they can take on all kinds of geometries. So we can set up rhythms where we have kind of single folds, right, that make just very simple triangular shaped beams. We can make them so that they go in sequences. So here you can see we've got folded plates that go in opposite directions. So we've staggered the module a little bit. We can do things like add folds to them that give these crickets that allow for slightly better drainage. And we can also conform folded plates to longitudinal structural geometries, like in this case you can see an arch. So here we're hacking together a couple of different ideas, right? It's kind of a beam arch, very, very shallow arch, so it'll still take some bending, but we're basically making that folded plate now kind of shaped so that it gets out of the way of the tensile region on the bottom of the beam, right? This is going to be more in compression than in tension. That's kind of one little hack that we've done. We've made the beam into a beam arch. And then the second hack is to make that beam up not out of a solid, heavy material, but out of these thin, lighter weight folded plates, right, that take away most of the dead weight and allow it to span quite a bit further. So in practice, you can see that we can do very, very simple folded plates. Here again, just a really basic triangular shape, and you can imagine that each one of those triangular folds is spanning from those columns all the way back to those columns there. A couple of interesting things to note about this structure. You can see right here that edge stiffener beam. That's the thing that's preventing the plate from flattening out, losing its depth, losing its section modulus. And you can see too that where the plate is functioning basically as a web instead of a flange, again, near the neutral axis, the architects and engineers here have actually sliced out pieces of the folded plate so that they can bring daylight into what's probably a warehouse or a factory building. And that, again, takes some of the principles we were talking about last time, right? The hacked beam, the castellated beam, taking material out from around the neutral axis, leaving what are essentially the flanges of the folded plate, the top and bottom fold. So taking away some dead weight that's not doing very much, and at the same time introducing some daylight into the space below. Another strategy for doing this is to realize that the folded plate can take on almost any geometry. And so if we really want to, for instance, bring in north light to, say, a factory building, we can design a folding plate that's tuned very closely to that functional need. And this checkmark shape, even though there are more efficient structural shapes that we could use, right? This is pretty far from an I-beam in terms of the efficiency of where its material goes. If you think about what that structure is doing, now it's doing a handful of functions. It is spanning from column to column, so it's got a structural function. It's keeping the rain off of that space, right? It's functioning as a roof. This area is not only functioning as the tensile flange, right, the bottom flange of the I-beam. It's also functioning as a gutter to take rainwater off and over the edge of the building. And you can see here the gap between the kind of low flange of this folded plate and the top or compression flange of this folded plate. There's a gap there that allows them to bring in daylight. So even though it's not a particularly efficient section, right, if we're comparing section modulus to the poundage of concrete that we're using, we could certainly span that more efficiently. But the folded plate is doing three things at once. It's a structural element, it's an enclosure element, and now it's also a daylighting element. And structurally, the plate doesn't really care what shape it is, right? The efficiency is just about reducing the amount of material that we need. All the plate kind of feels is that it's got a compression area there, a tension area there, a web in the middle that handles the shear between the two. So it's happy, right? It is going to work as a beam. Maybe somewhat limited in its length, the shallower it gets, but it's going to work as a beam, right? It has enough depth to carry a load over a span. We then are interested in how that fits in a whole range of potential functional considerations, right? Structure, but also rainwater and daylighting. And that can be any shape at all as long as there is some depth between the top and the bottom of the plate. And we put enough folds in it to keep it relatively stiff, prevent it from flattening out. Architecturally, there are all kinds of possibilities here. When we start to think about more complicated folds and shapes, we start to realize that we can impart a real architectural grain to a space below. So here again, we've got that idea about a beam arch, right? A beam that's kind of curved so that it puts more of the structure into compression than into tension, kind of gets out of the way of the tensile area. This gives us a taller space in the middle. If this is a factory, maybe we tune that to the size of the machinery that we have. Or if it's an assembly hall, right, this is good for both the acoustics and the sort of architectural character of the space, right? It breaks that long span down into something that's much more finely scaled. And here are some examples of that. In the 60s, it was really popular to do this for ecclesiastical architecture. Something about the folds recalls in a way that kind of Gothic combination of long span and very, very ordered, very, very apparent structural order to the space below. Here you see this is concrete, a few inches thick, or a few inches in terms of its thickness, but many, many feet in terms of the depth of that fold. And you can see deeper here at the edge, skinnier at the top. So in section, this is working really as a three-hinged arch, right? That has a place where it can rotate at the bottom, a place where it can rotate at the top, and these folded plates, the folded plates on the other side, are kind of leaning against one another at the top, stabilizing one another at that top ridge. We can tune the folded plate too so that we can bring equipment or people in not just from the ends, like in the kind of basilica plan, but also from the sides. And here you see sort of clever solutions about taking the folds not only across the span, but also using the folds to create what are basically columns And the geometry of this is such that we get a very good portal frame shape out of it, right? Deep at the corners, shallow at the bottom and at the top. So again, kind of like a three-hinged arch. And you can see here that those folds allows for some triangular openings on the sides, right? Resolving all of those forces down these compression elements into pin joints at the base, and then opening up spaces in between. So here now we have a folded plate that's responsive not only to the structural consideration, maybe also to the architectural consideration, the long span here, but also to circulation and servicing. Accessible not only from the end, but also because we're using the geometry to open up spaces on the side, we have lots of opportunities for bringing in equipment or vehicles or people all around the perimeter. Maybe the most dramatic recent example of this is this well-known ferry terminal by Foreign Office Architects in Yokohama. And again, they're using the kind of freedom of the folded plate idea to not only span across a very large area, right, the kind of waiting room or ticketing hall down here for the ferries themselves. That's a big span, 120 feet. But they're using the strength of the folded plate, and here you can see deep here getting a secondary kind of fold module there and coming down on the side. So it's got this kind of, again, like a beam arch, a shallow arch that works in bending, but also mostly in compression. They're using the strength of that to put a pedestrian roof over the top of it. And then in the longitudinal direction, they're tuning all of the folds to provide ramped access up and down to the terminal itself. So using the flexibility of the folded plate principle, every bit of the structure here, again, is on a fold, right? So everything has got that kind of flange and web relationship, right? That kind of structural depth. But in the longitudinal direction, tuning those depths so that you can get accessible slopes all over the surface of the folded plates. And the kind of genius of this is that there's an interior that's defined by the grain of the folded plates, and there's an exterior that lets people walk all over the building, right? Using the structural geometry, combining it with the kind of circulation that they wanted all over the top of the roof. Here you can see the interior. There's a kind of finished ceiling put on all the folds, but very definitely that folded plate geometry is what is defining the architecture on the inside. And you can see, again, this is one of these that has a sequence of modules, right? So deep fold here, as that shallows out, there's another deep fold that starts here, and then that sort of blends into a fold again along this line that opens up again. So there's always structural depth to the roof. It's just that it alternates modules longitudinally as you go along the ferry terminal. And closer to home, here's a more classic one that is more, I think, what we think of when we think of typical folded plates. This is a church in Collegeville, Minnesota by Marcel Breuer, engineered by Pierluigi Nervi. And you can see Breuer is very interested in using the folds not only to span the space, but also to really define the architecture. And Breuer, being a good brutalist, is going to show you every bit of the concrete formwork that went into making this. Notice too that this again is a portal frame, right? Pins down here at the ends on this giant transfer beam, and then great depth up at the corners where the bending moment is going to be the greatest. And what's happening here really is that the girders, the folded plate girders that span the space, merge into what are essentially folded plate columns that support them. And this, of course, is all one monolithic structure, right? The column sort of fades into the girder structurally through that corner joint. But everything, because it's folded, has a depth that can be tuned to whatever the structural need is. And you can see that the structure is kind of a consistent depth, or the fold is a consistent depth going across the top. And the columns then taper as they come down to what are essentially pin connections on the transfer girder below. Here, the construction shots you can see as they're building the formwork, I think you get a sense for the way the structure works really well. Again, in each one of these girders that's being poured across the top, you can see there's going to be basically a compression flange along the top fold and a tension flange along the bottom. And then that flat plate is going to work as a flange toward the top and bottom, but more and more as a web toward the middle. Here, pouring it, reinforcing, this is the formwork behind, and you can see the depth of that formwork. This is basically going to function, these vertical ones are going to function as columns, and you can see that they taper as they come down to the base. It's the right form for a three-hinged arch. And here at the same time that Breuer and Nervi were doing the church at Collegeville, they were doing the UNESCO headquarters in Paris. And this one I think is particularly brilliant because you can see the folded plates here, right, very clearly, bathed in this kind of weird blue light. But you can see that there's also this slab that runs between them, and that slab is this curved line right here. And Nervi arranges that curved line so that it is putting more material in the compression area of the basically long-spanning girder at the top here, coming down and being in the tension area as it comes over the supports, and that is tuned again to the moment diagram. That slab is a stiffening slab that allows the folded plate more capacity and compression. And therefore, as you go over the center of the span, it's going to be at the top. Continuous span, the compression is going to be at the bottom over the supports. You can see that that slab is kind of tuned to run from the bottom of the folded plate all the way up to the top of the folded plate, where the bending moment is going to be at its greatest. Otherwise, though, this is a fairly simple scenario. Compression elements at the top, over the center of the span anyway, tension elements at the bottom. That flips around, of course, when you go over this support here. But you can see that in both cases, Nervi has actually delineated a little bit where the flanges are, the concrete kind of thickens up, and then the plates themselves are basically functioning as webs. And you can think of these again as I-beams. Flanges up here, down here, and webs there and there. Okay, in the next video, what we'll do is we'll talk about what happens when folded plates are curved instead of just folded. And even though the principles are sort of all the same, we're going to make a couple of kind of fine distinctions between what we call short vaults, which are actually not folded plates, but instead are form-active structures, and true what we call long vaults, which are basically folded plates on a curve that function in the same way, right? Separating tension and compression in a spanning element, but do it along a curved surface instead of a folded one.